the format of the exam, you can see right in Blackboard the previous year exams are there. So the format will be exactly the same. Again, I don't give any trick problems, right? Problems are similar to what we discussed, what we solved, similar to homework problems, problems which we solved in class and in lectures. Also, review clicker questions from our classes, all right? Because multiple choice questions are quite often from there, right? Or very, very similar. So, if you know how to solve those problems by yourself, that's the major point, by yourself without having anything in front of you except for formulas, you should ace this exam, right? But it doesn't mean that it's easier. Don't feel relaxed. All right, formula sheet will be attached to the exam paper. You can disconnect it, right, and after the exam you can trash the formula sheet, right? And the formula sheet again in the Blackboard. You can see what will be there. Right? Then what else? What else? Right. Yeah, don't forget remember your recitation section number, because after the exam you will be supposed to put your exam paper in the proper envelope, right? Section 201, 202, and so on. Of course, there will be rosters. You will have to sign a roster and submit your exam paper, right? And also, you can use the roster to check if you are actually in that section. Okay, so then, any questions about that? Okay. Yeah, after the exam, I will send you my PDF file of my notes, right? Then I will try to make a video, right? If my camera doesn't go to sleep, because it tends to do that. Okay. Although I removed the sleeping mode, it's still, after half an hour, still on but stops recording. Olympus, what can you do? Okay, so first I will just review all major points that are going to be on the exam. All right, and then over here we will start discussing particular problems related to those major points. Right? Okay, I will grab my notes. Should I speak louder? Or you can come closer, right? And again, if you feel like something it's difficult for you to see, just move around, right? So I will start the review with vectors. Right. So let's assume that we have some vector, and of course we need to introduce a coordinate system. Let's say this is my y, right, x, and let's assume that we have some completely arbitrary vector a. Which way? Okay, small one, vector a. Right, so we need to write it in a component form, and I want to write it using unit vector. Unit vector along the x-axis. How do we call that unit vector? Along x-axis. What? Sounds too complicated. It's just I hat. You remember, whenever you see symbol with the hat on top, it's a unit vector, most likely, right? Unless they used it for something else, but most of the time it's a unit vector. X-axis, along x-axis, I hat. What is the value of unit vector? 1, all the time. Don't think, just 1, right? Its role is just to show that is our positive x direction. That is our positive y direction. It's positive z direction. That's the only role of those unit vectors. So I hat. Okay, I will use probably green. So unit vector I hat. Then in the y direction, unit vector, how do we call j hat? Right. Okay. Sooner or later you will get used to this. That common, very common, ridiculously common notations. Right. And so we need to find components. First, let's draw component vectors. Just draw a normal line, perpendicular line to the x-axis, for example, right? And this will be our, what is called component vector. Component vector, right? That will be our a sub x component vector. Right? And then if we want to find a sub y component vector, again, draw a line which is perpendicular to the y-axis, and this will be our a sub y, again, component vector. And usually one of the angles can be given. So let's use conventional way of measuring angle. You remember conventional way? From plus x-axis in the counterclockwise direction. So let's label it theta. Okay, and now if we want to know components, right? Just basically the length of the component vector. A sub x equals to. Of course, we just need to use property of a right triangle. A n times which function? Cosine function. If you want to find side which is adjacent to the angle, you need to use cosine. Remember this, right? Cosine and sine. I think in the formula sheet now I started showing that, right? So somewhere at the end of the formula sheet you can find those, right? Probably. A cosine theta, right? In this case, this component is positive because a sub x points in the positive x direction. If our component vector a sub x pointed in the negative x direction, component would be negative, right? Yeah. You wanted to say something?
Are you using a vector sign for that?
No. Over here.
Yeah.
No, right now, okay, there are two different terms which this book uses. Component vector, it's a this. But the length of the component vector is a component. So right now I'm writing a component, right? Which is basically the length of this component vector, but you need to also remember if it points in the negative x direction, our component is negative, right? So I didn't make a mistake. Right, and then of course a sub y will be a sine theta. And then of course we can write in terms of unit vectors, a will be equal a sub x I hat plus a sub y j hat. Okay, so that's how we can find components. And if you have two vectors presented in the component form, and let's say we want to add them or subtract them, what do we have to do? We just need to add corresponding or subtract corresponding components, x components or y components. Right? Okay, let me write something like this. Let's say we have two vectors and we want to add a plus b. In a component form, it will be just a sub x plus b sub x in the x direction, and a sub y plus b sub y in the y direction, right? So that's the beauty of writing vectors in the component form. It's so easy to massage them. It's so easy to do anything you want with them. Okay, it's enough about vectors. We will practice a few examples. We will look at a few examples. For now, let me just separate it. First part. Now, after this, we went to one-dimensional kinematics. What? Something? Again, guys, if something not clear or you want to say something or ask something, just do it, right? Okay, so then one-dimensional kinematics. Okay, so one-dimensional means like a car moving along a straight line or a train moves along the railroad. In this case, we just need one coordinate x, which changes with time, right? And you remember we have three levels of kinematic quantities: position, velocity, and then the deepest one, acceleration. So if we want to go to the second level, what do we have to do with the first level? Differentiate. We need to take a derivative. So if you want to know how fast x changes with time, which is the velocity, which can be a function of time, dx over dt. So we went to the second level. And then if you're interested how fast velocity changes in time, again, differentiate. When you dive deeper, differentiate. So acceleration, again, it's possible to be a function of time, dv over dt. And now graphically, what do we have to do to make these transitions graphically? Let me plot first x versus time, then there will be v versus time, and then I want to plot a versus time. And let me draw some completely arbitrary function, I don't know, let's say something like this. How can we find velocity at this point graphically? How can we find graphically velocity at that point? Graphically, we need to, we're not going up, we're still going down. It's basically what I wrote here mathematically. Now I try to draw graphically, right? Slope, tangent, slope over tangent line. Draw a tangent line at that point, and that will be our velocity, instantaneous velocity. Okay, I will probably use red. So tangent, right? Okay. And velocity equals to the slope, right? Slope of that line. Right, and let's say you explore velocity at each point, and let's say you plotted something like this, right? I know. Right. For example, right? I'm just making it up. So now, how can we find acceleration, for example, at any point? Again, draw a tangent line, find the slope, and that will be an acceleration. Again, acceleration equals to the slope of the tangent line, slope of a tangent line. Again, guys, if something not clear in terms of my handwriting, say something quickly, right? So which where this?
No.
This? The equation. A this or the
Yeah.
A as a function of time. A as a function of time equals dv over d. Come on, it's a good looking d. At least I like it. Right. And of course, then if you again look at instantaneous acceleration at any point, you can find maybe that plot can be something like this. Actually, speaking of acceleration, over here, acceleration positive or negative? Positive, because slope is positive, right? And here acceleration will be negative because the slope is negative. Okay, let me at least here match them, right? And then there will be drop and negative acceleration. Okay, so that's how you can do it graphically. And then, let's say if you are on this level, on the velocity level, and you want to find distance. So how can you find that? Distance covered by an object. You already answered it.
Oh, area under the curve.
Because area under the curve. If you want to move up between these three levels, acceleration, velocity, position, if you want to move up, you just need to calculate area under the curve, right? If you are in the position, in the velocity level, plot velocity versus time, calculate area, it will give you a distance covered by the object. We never tried to go from here to there, so most of the time transition from the velocity level to the position level. Okay, let me mention this. All right, so if I plot v versus time, and let's say this is t initial, this is t final, and some completely arbitrary curve, let me draw something. All right, okay, so distance covered by the object between initial moment of time and final moment of time is this area. So let me use red. So this will be, okay, so area equals to, it's a one-dimensional, it's actually it's a displacement, right? It's a displacement. Okay. So that's one-dimensional situation. Now let me separate it a second. And after this, we introduced kinematic equations, which we can use to predict the future of the system, right? If you know some initial conditions, you can predict the future. When can we use kinematic equations? Actually, today in the morning we had a PhD qualifier exam for students, and sometimes some students still, even in grad school, try to use kinematic equations under the wrong conditions. All right, so when can we use kinematic equations? Yeah.
Sorry.
Punishment for not seeing the beauty of my V. All right, so when can we use kinematic equations? I mentioned many times during constant acceleration, right? I will keep bugging you about this, right? Whenever we will have to use kinematic equations, I will be asking this question because yeah, it's very important, right? It's illegal to use those equations if acceleration is not constant, right? We derived them for that situation. Okay, so one-dimensional. Let me just write them. So kinematic equations, one-dimensional. So I will start with first one, velocity. V equals v naught plus Force of habit. Now instead of a, I use alpha. Rotational motion. All right, at. Then second position. X equals x naught plus v naught t plus 1 over 2 at squared. Good? Okay, so in both of these equations there is time. But the last equation, the special feature of this equation, that time is removed. We just combine these two equations in order to write down the last one, just to simplify our life. So v squared equals v naught squared plus 2a x minus x naught. So this is a set of kinematic equations. Again, if something not clear, say something immediately, right? See something, say something, right? Yeah.
I have a question. With regards to finding the area under the curve, would it be more appropriate to use an algebraic method, like dividing it up into shapes, or can we use integration?
It's up to you.
Okay.
Again, since I promised to you not to go into calculus, although it's a calculus-based course, but when students come to Physics 1, their level of preparation in terms of calculus is quite different. Some of you are very comfortable in terms of integration and differentiation. Some of you never seen that. So as a result, I just use it in classes to derive something, right? But when we start solving problems, we usually just calculate areas. But if you want, you can integrate it. But usually all the time it's a straight lines, right? So calculations, calculate area is easier way. Yeah.
You say v naught or x naught for curve clarification. That refers to like additional, right?
Yeah. Again, the goal of these equations, they allow us to predict the future of the system, right? Position, dynamics, right? So once you know these initial values, right, in acceleration, you just plug time, get the future. Plug time, get the future. Okay, so let me frame them. All right, so we're going to use them. Actually, let me get for case when there is acceleration due to gravity in the case. Let me just mention it quickly. So if you have, let's say, y-axis up, all right, and the second case will be y-axis is down. Right, this is y. And let's say acceleration due to gravity is not, let's say acceleration due to gravity is down, right? Not let's say g, right? And here acceleration due to gravity is g. So, but if you want to use this equation for the one-dimensional motion in the y direction in the presence of gravitational field, then our accelerations will be, in this case, in the first case, a equals to what? Negative g, because again, acceleration is a vector. Positive vector just means it points in the positive x or positive y direction. Minus g, negative vector, just means it points in the negative x or negative y direction. In this case, g is down, y is up, so it's a minus g. In this case, of course, it's just g. Okay, and now let me separate it from the rest. And now, after this, two-dimensional motion is just basically, again, application of these equations along the y and x direction at the same time. What is the acceleration if we have projectile motion? If we have projectile motion, what is the acceleration in the x direction? Zero. Since we neglect air resistance, we assume that objects are rigid, small, right? So the air resistance is can be neglected. And then, of course, out of these equations, only one equation survives this, right? So this will be 0, and we will have x equals x naught plus v naught xt, right? This will give us very important piece of information that during this motion, x component of the velocity exactly the same throughout the whole motion. If we have 5 meters per second at the very beginning, it will be 5 meters per second at the very end, right? But in the y direction, since acceleration is not 0, we have to deal with all these three equations. Okay, so now rotational motion. Okay, so now rotational motion. Okay, I will probably draw some simple picture. Maybe over here. Okay, some object, a point, moves around the circle. For the sake of convenience, I still write down or draw y and x axis, although we don't use them to describe rotational motion. More convenient way of describing this motion if we use what is called polar coordinates, r and theta. But r in this case is constant, right? So r is constant, so what we just need to know are theta, right? Theta. Okay, so let's assume that our object, if our object move from this point to this point, r is constant. R is constant. Conventional way of measuring angle, theta, right? And now, before I start writing two approaches that can be used to describe rotational motion, how did we define angle in radians? Do you remember? How did we define angle in radians? How can we find it? This angle in radians equals to, you have to just take this arc length and divide it by the radius, right? Okay, let me write it over here. Theta in radians equals to arc length, this arc length, divided by radius. Okay, I will put 3 lines by definition. Every time you look confused, staring at my handwriting, right? Is everything good? Yeah. Still? Because now I'm looking at you, you're still staring at my... You make me feel awkward. Not awkward, okay. Yeah. So, what I wanted to ask you. So, what is inside of radians? No. 2 pi. It's just a number, right? Inside of radians. Look, by definition, meters over meters means in the radians there is nothing, empty, right? We just use radians to remind ourselves. We measure angle using these fancy units, kind of unit, but it's dimensionless. Okay, and now there are 2 ways of describing rotational motion. So let me write the way I presented the table in one of the lectures. So first, angular description. Let me description. All right. Then there will be linear description over here. Right. Okay, let me separate them like this. Maybe it's too much. Let me increase number of things over there. Okay, so what do I mean by angular description? This rotational motion we can describe by using this r and this angle theta. Right? Basically using just angle. So position, I know, pi over 3 radians, pi over 6 radians, pi over whatever, right? Angle can be used to define position of this object, right? So over here, first I will write theta angle, right? Okay, if we use theta to define position, then of course next question, how fast this angle changes in time. Which quantity I'm talking about? How fast angle changes in time?
Angular velocity.
Angular, keep adding angular now. Angular velocity, angular this, angular that, right? Angular velocity, how fast theta changes in time. Omega equals d theta over dt. Angular velocity. Right. Again, I'm just waiting for the right person to respond. So you see, we're moving from the position level, angular position level, to the velocity level, differentiate, since we're going deeper between these levels, like position, velocity, acceleration. So we differentiate. And then if you want to know how fast angular velocity changes in time, which quantity is that? Angular acceleration, right? How fast angular velocity changes in time. We're using alpha, d omega over dt. So that's angular acceleration. Angular acceleration. Okay, so that's how we can describe rotational motion using angular quantities. Now, linear. You can achieve exactly the same by, for example, defining position of this point using this arc length instead of this angle, right? They're connected, right? So we can use arc length, S arc length. And then here I want to write linking equations. Equations which connect this approach and this approach, these two descriptions. So how can we find S if we know, for example, angle? Which equation links these two ways of defining position? Yeah, it's pretty much from the definition of radians. S equals r theta. Okay, so let me some different color. All right, so it will be S equals r theta. These two descriptions are connected through radius of this orbit. Let's start with vectors. Vector algebra, just to refresh vector algebra. I will put the first bullet. Okay, complicated trip of a car. So there are a few legs. First it drives in one direction, then drives in the other direction, then in another direction. We will have to find the total displacement. Right. Okay, I will first draw a coordinate system. Right, something like this. So this will be my y. This will be my x. So we have some car travels. A car travels. So the first leg of this trip, car traveled 620 meters that way. Basically along x-axis. which color? Okay, I'll use black, right? So first part of the trip, D, I think it's D1 I label it. Yeah, D1. The length of this is 620 meters. So let's write in component form each of these vectors, and then at the end we will find the total displacement. So components of D1 will be, let's write in using I hat and J hat notation. X component will be 620, right? The whole length. Is it 620? Yeah. So it will be 620 I hat, and displacement in Y direction 0. So it will be just plus 0 J hat. Then second leg. It says the second is 440 meters at 30 degrees below plus x-axis. 30 degrees below plus x-axis. So which quarter of the coordinate system? The last one, the fourth one. Of course, you can draw it here, starting from the origin, right? That vector. But you remember, vector can be moved, all right? If you preserve its direction and length, you can move it anywhere you want. You can position it here, here, there, anywhere. So let's just position the second vector, the tip of the, the tail of the second vector to the tip of the first one. All right? That's how we add vectors graphically. So I want just to follow graphical way of adding vectors. So 30 degrees, so it will be something like this. Right. So let's say this is D2. And this angle is 30 degrees below plus x-axis, like something like this. And the length is 440. Maybe I will write something. Which way I should write it? The absolute value of D2 is 440 meters. Okay. You know these notations, right? Vector in vertical brackets, it means just the absolute value, the magnitude of the vector. Right, so let's write it in components. D2x. Using this, draw a normal line, perpendicular line to each of these axes, right? It will give us component vectors. So this will be right, and this will be, so this will be D2x, and this will be D2y. What will be the value of x component? Not the value. How can we find x component of this vector? No, not Pythagorean, close to that. Basically, you just need to work with this triangle. This point, this point, this point. It is a right triangle, right? So I ask you, what is this, right? So how can we find the length of this D2x? Hypotenuse, right? Times which function? Not 30 degrees. Cosine or sine? Cosine. Since we want to find adjacent side, cosine function must be used. Again, if you're not confident, look at the formula sheet on the exam. Right at the end of the formula sheet, it's given. Don't make this unnecessary mistake. So D2 times cosine 30 degrees. Is this component positive or negative? Positive, because component vector points in the positive x direction, right? So the component is positive, so plus. Then D2x, and D2y. Now obviously it must be, sine function must be used, right, in order to find this opposite side, right? Opposite side. Sine.
Wouldn't it be 330 degrees because
Okay. you want to use the conventional way of measuring angle. Nothing is wrong with that. You can do it. I would most chances that I will use that angle minuscule. I just don't trust myself in working with the calculator, calculating some this big angle. I better calculate angle of some angle which is less than 90 degrees and then manually adjust all those pluses and minuses. That will be my approach. Right? But what you said is absolutely correct. So, and if you use your approach, all pluses and minuses will pop up automatically. You don't have to think and look at the picture. But in this case, since we don't use a conventional angle, so what do we have to add? This component, positive or negative? Negative, right, negative. Because this component vector, you see component vector, it points in the negative y direction, So we need to add minus, okay, let me use red color, emphasize, right, negative y direction. Okay, so now as a result, we can write in this notation d2 vector equals to, actually we can calculate it, but I'm not going to calculate, I will just write down the answer. Right, so it will be 381 meters, 381 and minus 220 meters. Okay, so as a result, we can write this plus, okay, let me write minus 220 in j hat direction. Okay, so now the last leg of this trip, 550 meters and 60 degrees below minus x-axis. 60 degrees below minus x-axis. Again, if you draw it from the origin, it will be something like this, right? But again, you remember, if you preserve magnitude and direction of the vector, you can position it anywhere you want. And our graphical way of adding vectors, we need to position the tail of the previous one to the tip, the tail of the next one to the tip of the previous one. Okay, so as a result, I will draw this last one, and if it were here, I move it, and it will be approximately this way. Right? So 60 degrees, okay, roughly. So this is D3. 60 degrees below my minus x-axis. Okay, I will draw this horizontal line for the sake of convenience. Right. And where is my 60 degrees? So this, right? This angle. So this will be 60 degrees. It's given 60 degrees. Okay, so now let's find first component graphically. Draw them, right? Component vectors, and then right. So in order to find x component vector, this d3x. Everyone agrees about this? Basically, I just projected this vector on the x direction, right? If you're still confused, you can take this vector, position it here, right? And this will be our d2x. It's exactly the same, this with that. Right? Okay. All right, so now d3 y will be that, or you can draw it here as well, right? Position it there or here, it's exactly the same. Again, you remember you can move backwards. So this will be d3y. You're so quiet now. I'm doubting. Is it too simple, or are you confused, right? Following, right?
It's not this confusing. It seems like a lot to remember.
No, it's not a lot. With this course, Physics 1 Mechanics, it's all about vectors. We're going to do that almost every class. Decomposing, combining components. That's why we spend so much time on vectors, right, and the components, right?
So is D2y and D3y the same?
D2y and 3y, no, not the same. Lengths are different, angles are different, right? So not the same, right? Yeah.
Clarification, when it came to like D2x and D2y, when you were plugging in D2, you'd plug in the 440.
Yes, the length, right? The length. In this case, it's basically hypotenuse of that right triangle, right? Of this right triangle. Right? Okay, basically I use this, right? But of course, since we don't use a conventional angle, we have to be careful and look at the triangles, right? And use properties of right triangles. Yeah.
Just to clarify, what do you like the graph convolution?
Yeah. Now I'm listening.
I'm sorry. What exactly did we like the graph? What were we trying to find exactly?
Eventually, we want to find the net resultant displacement. So we will have to add all these three vectors, right? So we will have to find components of the resultant vector. So like, for example, if I first travel this way, then travel this way, then travel that way, what's my total displacement, net displacement? Final point, initial point, vector, right? Yeah. So that's what we're trying to find. Right. And I'm drawing it in order to show it graphically. Right, and then of course we will work with components in order to find components of the resultant vector. Okay, so now let's find this d3x, and okay, let me maybe frame this. It's my second vector. This is my first vector, and now the last one, d3x. Of course, it will be d3 times cosine, right? Cosine function. Cosine of 60 degrees plus or minus because the component vector points in the negative x direction. So you see this component d3x points in the negative x direction, so we have to put minus manually. But if you use conventional angle, minus will appear automatically. Right, okay, the answer, this is minus 275 meters. Minus 275 meters. And then d3y equals. Now obviously cosine function must be used if we use sine function. Oh, the cosine before, now it's a sine function. d3 times sine of 60 degrees. Working with vectors is a little bit tedious, right? But that's how we model the nature. God created this nature this way, and now our work is just to model it, right? And that's what works.
What is D3y negative?
Okay, that's my next question. That's why now I started walking towards you. Is it positive or negative? And you see, on purpose, I left some space. I prepared myself, right? Negative, of course, now negative, right? So again, negative y direction. So the answer is minus 476. Minus 476 meters. Okay, so now we have all ingredients. Now we just need to add these three vectors, right? So d total equals d1 plus d2 plus d3. Whew. Graphically, where's the resultant vector? It starts at the, okay, let me erase this vector over here because it can distract us, right? It starts at the tail of the first vector and ends at the tip of the last vector. And order which you use to add these vectors doesn't matter. Your answer will be exactly the same. Right. You can add d2 plus d1 plus d3 or d3 plus d1 plus d2. The answer is going to be exactly the same. Right, so the resultant vector is this. So this is our d total. So we just need to find its components. And mathematically, we just need to add corresponding components. X component, and X component. Add them all up. All right, so it will be, I will write here, so it will be d1x plus d2x plus d3x in I hat direction, positive x direction, and then plus d1y, d2y plus d3y j hat direction. I'm not going to write numbers, right? Because don't forget about minuses, right? I will just write down the answer. So as a result, you're going to end up with this 726 meters. That's the total displacement in the x direction. All right, and in the y direction, 669. Wait, no, 696. 696. Has it displaced in the positive y direction or negative y direction? Negative y direction, right, relative to the initial point. Actually, it's visible, right? So it displaced in the positive x direction and negative y direction. Now, let's find magnitude. So magnitude of d total. Okay, I will put an absolute value sign. I'm kind of even afraid to ask you, like kind of insulting, right? All right, Pythagorean theorem, right? dx, d1x, or d total x squared plus d total y squared, right? So square root of d total. You know what? I will just use x, dx. Dx without any additional subscript squared plus d y squared. So that is our dx, and this is our dy with minus, right? So, although here it doesn't matter since we're squaring it. So the answer is going to be 1005.7 meters. Okay, too many Sig Figs, but you can drop more. Right, now let's define its direction. You can use any angle you want. I will probably use this angle. Let's define it position. I mean, not position, direction. Direction. Let's define this direction using the angle phi. So how can we find this angle phi? You see, phi. It's the angle between x direction and our resultant vector. How can we find that angle? We've done it a few times, and now we just need to recall it. Again, properties of right triangles here, right? They are everywhere, right? So look, what we found, what is this dx? It just, okay, if I drop this normal line, so this is my dx, right? Right? And this is my dy. I don't like that it's almost overlapping with the first vector, right? Right? So now you can tell immediately, right? You can tell. So how can we find that angle? Which function can be used? Yeah, you can. No. Yeah, Pythagorean theorem is not going to happen with the angle, right? Yeah, angle. We already applied Pythagorean theorem to find the magnitude. Angle. Use tangent. It's the most common way. Tangent of this angle will be what? Ratio of what and what? Properties of a right triangle. So if you have a right triangle, right? Let's say this is angle theta. How can we find tangent of theta? Let's say this is A, B, and C. Opposite versus adjacent. Of course, you all know that, right? You just need to apply it all the time, right? Because it's so tangent phi equals. Since we don't use conventional angle, I usually just use an absolute value. Just a triangle, length of this, length of that, drop all pluses and minuses, right? So opposite, it's dy divided by absolute value of dx. Right? Okay, if you do that, you will end up with phi will be approximately equal to 43.8 degrees. Okay, ladies and gentlemen, all right, so if I leave it this way, is it acceptable? I will confuse, of course, if somebody tries to read this, right, that person will assume that my vector is in the first quarter, but it's not the case, right? So we need to add additional piece of information because we're not using conventional angle. So I will write just below plus x's. Below plus x. Okay, so now it's done. It's a little bit tedious, but vectors are everywhere. Of course you can, what use calculators? To find immediately total displacement. No, if you write the answer immediately, I will not accept it. We need to see your work. Yeah. Yes, you can do that. Yeah, in this case, if you put a minus, you don't need to add anything else. Yeah, somebody else. Oh, yeah.
Tangent, what is it? Tangent of what?
Phi. Come on, guys. Looks like phi. It's Greek letter phi. Come on, guys. You're in science, right? You're an engineer. You need to remember by heart Greek alphabet. And sooner or later you will remember it, right? Of course, you will never be able to read anything written in Greek, but you will be familiar with all letters. Alpha, beta, gamma, delta, and so on. It's all Greek alphabet. Yes.
So if we were on the test and it asked us to find the direction that you want, you
yeah.
find the angle between the total and the original x.
Direction between. Okay, you lost me. Right.
So if they ask for direction,
yeah.
you want to look for like the angle degrees
yeah.
between the total.
If it depends on the question. If question asks you just find a direction without any additional instruction, then it's up to you which angle to use, right? As long as you would say that phi is, I don't know, measured from plus axis or minus x-axis, something like this. But if problem says direction relative to this axis, then of course you have to use that. Anything else?
When you're talking about the angle, like the final angle of D, could you use like clockwise or counterclockwise?
Yeah, absolutely. Again, if there are no any restrictions in the problem, you can use anything you want, right? As long as it will be a unique, right, angle to avoid any ambiguities, right? First, I mean, a little bit of. Can I start erasing this, guys? Quick review of a difference between distance and displacement. Very, very easy question. Let's assume that we have this y. Let's say this is y equals 0. And let's say we have some object which moves this way. It starts, okay, I use black, right? So let's say it starts from this point, which is y equals 1. It goes up, let's say this point is y equals 5. Then turns around and goes all the way to, let's say this point is y equals 3. Wait, not 3, sorry. Y equals minus 3, I think. Yeah, I just made up completely arbitrary situation, right? So first, can you write down what is a distance covered by this whatever object? whatever this system is. What is distance?
For the problem.
Yeah, with the problem. Okay, by definition, it's a total path length, right? Okay, so total path length in this case. So it moved up from 1 to 5. So it will be 4 on the way up. All right? And then it turns around and starts moving down. What's the distance covered on the way down? From 5 to 5. Oh, wait, from 5 to -3, it's 8. Come on, it's been a long day. I had 4 hours of qualifier exam in the morning. From 9 to 1, it's a PhD comprehensive exam, right? So, right, so what did I say? 8, right?
Yes.
Okay, 8, yeah. So it will be 12, right? So that's distance. Distance, is it a vector quantity or scalar quantity? Scalar, just a number. Total path length covered, right? Did I get the same? Yes, 12. All right, so now displacement. So displacement, you remember it has this boss's attitude, right? You don't care what you did and where you went, right? I just only cares where you were and where you are now, right? How much you sweat and how many sleepless nights you spent, who cares about it? It's your problem, right? Right, boss's attitude. So final minus initial. So what's the displacement in this case? Negative
3.
3.
4.
Good idea. All right, final point -3 minus initial point. Initial point is 1. So -3 minus 1 minus 4, -4, right? Okay. So displacement will be again, so let me remind you, final minus initial point. Again, it doesn't care what system did between these 2 points, only about final and initial point. So it will be -3 minus 1, so it will be -4, whatever units, meters, kilometers, centimeters, right? The same in the x direction, right? So I just wanted to remind you about it. What is a displacement of the Earth after 1 year of moving around the sun? 0, because initial and final points are the same. Okay, neglect the galaxy moving, right? So that's stuff, forget it, right? So 0. But of course, distance will be here, tremendous distance will be, right? Now it's 5. Okay. Okay, enough of this. Come in order. Adding and multiplying numbers with Sig Figs. Let's refresh it. Okay. I will erase this now. Quickly, one example from each part. Separate it this way. So let's add 1.53 plus 2.786 plus 3.3. If I use my calculator, it gave me 7616. Again, I immediately cross it out because it doesn't make physical sense. When you add numbers, which rule do we have to use? Again, philosophical idea, we just need to look for the weakest link in the chain. And the strength of the weakest link determines the strength of our final answer, right? So, the weakest link, in this case, we just need to look at the least certain number. Least certain number. Here we have uncertainty in the 3rd digit after the decimal point. It's the strongest number, right, in terms of accuracy. This 2nd digit after the decimal point, it's sort of in the middle. And this is our weakest link. It's the least certain number out of these three. So this is least. Okay, you know what? Let me underline this, because that's where uncertainty is, right? You remember? According to the convention, uncertainty is in the last digit. So this is the least certain number, the least certain number. So uncertainty of this number determines the uncertainty in our final result. So it means that uncertainty in our final answer must be in the first digit after the decimal point, right, in the first digit. So it must be over here. Again, it doesn't mean that you just drop the rest. In this case, it is actually. But if we were here, let's say, if we had over here, like, let's say 5, we had to round it, and we would have to add additional 1 to the previous digit, right? But in this case, it is approximately 7.6. So you see, this uncertainty was transferred, this level of uncertainty is transferred into our final result, right? So that's how we add, subtract numbers properly. Now, multiplication and division, one example. 1124, let's say we multiply it by 1.95. Again, my calculator gave me 2192. Immediately I will cross it out. When we multiply and divide numbers, so what do we have to look? How can we find, how should we find the weakest link?
You look at the digit with the...
Yeah, we need to look at Sig Figs, right? And the number with the least number of significant figures determines the number of significant figures in our final result, right? In this case, here we have 4 Sig Figs. Here we have 3 Sig Figs. So this determines number of significant figures in our final result. And again, we need to round the number, right, to 3 significant figures. So in this case, just 2 will be dropped, right? If we had here 5 or 6 or 7, right, and then of course we will have to add 1 to this, it will be turned to 0, and then 1 will be added to the previous digit. So in this case, it will be 21.9, right? 3 Sig Figs, right, which is determined by this number. Okay, good. Refreshing this. Now, next. How should I phrase it? No, probably I'll show you motion, and then we need to find which curves describe this motion. Let's say I have this ball, and I throw it down. It hits the floor, and then it gets back, right? Bounces back. So I'm going to plot V versus T graphs, and we need to find the right one for which describes this motion. So we just practice how to connect graphs with physical situations. Okay, so first I will draw a physical situation. All right, so this is another question. So y-axis I picked upward. So let's say y, this is ground, this is 0, right? 0. And the ball moves first down, then it hits the floor, and then it will go up. The process of hitting the floor, it's complicated. We're not going to discuss that. We just assume, so first velocity is that way, and then suddenly velocity is just upward, right? Yeah, because collision, yeah, it's... we discuss kinematics, we're not discussing interaction. Right, and a few plots. Okay, I will just use one color for the sake of simplicity. All right, so what we are plotting, V versus T. V versus T. V versus T. This is on my V. Right. So this, oh my god, even this, then this, I ran out of lots, right, and now so which graph out of these 1 to 5 describes this motion, and y-axis is upward? What? The last, which one? The first one? Okay, some people vote for the first one. Huh? The last one, people think, right? The fourth one, 1, 2, 3, 4. All right, the fourth one, you want the fourth one? There are 2 for the fourth one. All right. But I don't know, are you trustworthy people? Right? Right. Okay, let's start discussing. Yeah, we have different. I want to say opinions. No, opinion is, yeah, it's important to have opinion, but it's better to have knowledge, right? Because sometimes you hear some opinions and you think, you know what? All right. That's why I like physics. It doesn't care about opinions, right? You have nature to control.
We assume that when they walk to the floor,
Okay, I just, in order to have a stronger effect, of course, let's assume it's dropped. It's dropped. Actually, even if I drop it, I mean, even if I throw it, it's exactly the same. Will be straight, right? It's not going to change anything in this plot.
if the floor is velocity zero,
Huh?
velocity is zero when it hits the floor.
I said let's just not dive deep into that interaction, right? It's complicated, right? There will be, of course, change in the direction of the velocity. Okay, so let's start one by one. First one, somebody actually voted for that, right? Why? Right. Okay, so first, velocity is positive or negative? Positive. What does it mean, positive velocity? It means it moves in the positive x direction, right? Velocity is a vector. Positive x direction, it means at the initial moment of time, it means moves up. Obviously not our case, right? But anyway, so let's go. Then it moves up, but velocity is going down, right? But it still moves up. It's just decelerating. Acceleration will be, of course, in the opposite direction, right? Because the slope of this curve is negative, acceleration will be negative, right? But object still moves up, so, but it's slowing down. Then at a certain point, what happens with the object? Physically, in simple words, it stops for a moment, right? Stops for a moment. Now velocity is negative. How can we call this point? It's a turning point. You remember the major feature of a turning point. Velocity changes its sign, right? If velocity changes its sign, it's a turning point. So basically this motion, it's this motion, right? First, large velocity, then object slows down, starts slowing down, just slows down, right? Stops for a moment at the top, and then changes direction of the velocity and starts moving down. So it's that case. Maybe I will sketch it, right? So it will be this motion, right? So this is the ground. Everyone follows? Awesome. Now this, no one voted for this, right? At least explicitly. So first part, exactly the same as here, right? So basically, it moves up to the turning point, okay, straight up to the turning point, and then it stops for a moment. Then, probably it's a rocket, it turns on the engine. And start accelerating again up. Start accelerating and starts moving up. Velocity again positive. It stops for a moment to turn the ignition, right? And starts moving up, right? Up to some jet engine. So it's obviously not our case, and then again it will keep moving up. So it moved up, and then again start moving. Stopped for a moment. This, again, first, no. It starts from 0. Velocity is positive. So which object can behave like this up to this point? Which object behaves like that? It's a rocket, right? It moves in the positive velocity is positive, right? Starts from 0, so the rocket was first standing on the ground, started accelerating, reach maximum velocity, and then something I cannot imagine, right? Suddenly, it changed direction of the velocity without stopping. It's an interesting situation, right? Nice idea for a Hollywood movie, right? Suddenly it stopped from large velocity, or suddenly it's in the. No, it's not. It's not changing. Come on, I'm completely. So what did I say wrong?
Because in consideration like outward.
Yeah, I was wrong, guys, right? I was wrong. So it reached the maximum velocity positive, and then after this point, velocity still positive, right? What I said was nonsense, right? Long day. Friday, that's my excuse, right? All right, so it still moves in the positive x direction, but now velocity is slowing down, all right? Slowing down. So first, it moved up to this point like a rocket, all right? And then it started decelerating, right? Engine is cranking down the power. So now it's moving slower and slower, but still moving up. But velocity is getting smaller and smaller, and eventually it will stop for, okay, I don't know. We don't know what happens after this, right? Oh, I'm surprised why I thought it changed direction. Sorry. This moves in the negative y direction, so it goes down, accelerating, then reaches maximum velocity in the negative y direction, and still goes down, but now slowing down, right? First it was speeding up in the negative y direction, right? Speeding up, and then it started slowing down, right? And eventually it will stop. Kind of strange behavior, right, of an object, normal object in gravity. So now let's look at this case. All right, so we dropped it. Velocity is negative, right? Velocity is negative. First velocity is 0. So my, yeah, I just released it, right? I should release it, right? I should release it. So I was wrong, right? So its object is released, moves in the negative y direction, accelerating, then hits the floor. All right, again, we're not going to describe what happens when it hits the floor, but it suddenly changes its direction. So now large velocity in the positive y direction, and it's slowing down. So it starts moving up, decelerating. So that's the right curve, right? The correct this, right? This is the right situation. Okay, so practice these situations, right? So you can connect real life with plots, right? Quick. What if we have something like this? Let me separate this. Let's say we have x versus time, and plot like this. Okay, x. In which direction does this object move? Plus x minus x. Huh?
Positive?
Positive. Direction of the velocity is determined by what, graphically? Slope, right? Slope, is slope positive or negative? For example, at this point, at this point, negative. So it means velocity is negative, it means object moves negative x direction. Or even just to look at what happens with x. First axis are 5, then 4, then 3, and so on, right? Obviously, it moves in the negative x direction, right? Okay. Then, additional question. Is it accelerating in the negative x direction or decelerating? What? Decelerating. Yeah, because the slope is getting smaller, right? So first it's steep. It means negative velocity is large, but again, negative, it just means it moves in the negative x direction. So it moves first fast in the negative x direction, then slope is getting smaller. It means it moves slower in the negative x direction. Right? So it's decelerating in the negative x direction. Moves in the negative x direction, decelerating. Or maybe I will write. It moves in minus x direction and it decelerates. And it slows down. And it slows down. Okay, crowded. Right. So, should we discuss these calculations of area? What? Or we can skip it. Okay, just one warning. So pay attention, what does the problem says? For example, curve can be from 0 to infinity, right? But if problem says calculate a displacement between, for example, 2 seconds and 5 seconds. So calculate area only between those two moments of time. If the problem says between 475 and 524, only between those. Don't just calculate whole area which is under the whole curve which is given in the plot, right? Just carefully read the problem, because I've seen this completely unnecessary mistakes, right? Only area between the plots, between the points given in the problem. Right? Okay, then I will send you my notes. You will see this. Right? So now let's look at projectile motion, two-dimensional motion. So the first problem, the situation is quite trivial, right? No obstacles, but I want to discuss all possible pieces of information about this motion. So the situation is this: somebody shoot an arrow, which goes from the ground, completes a parabola, and hits the ground. We only know the travel time and the angle at which object was shot or thrown, right? And we need to find a bunch of information. So let me just first draw a graph, right? So this will be, I will just put a new bullet. And should I label how is it? Okay, flying arrow. Okay, so first, nice parabola. Okay, big enough. Coordinate system is a must, right? And please, guys, I don't know why, but lots of you draw coordinate system like this, right? For example, like y. I don't understand why you draw this side, right? It's unnecessary. I asked actually Dr. Mittler, he's very familiar with the high school system and so on, and he was also surprised, right? So what you need, just name, direction, and the origin, right? Okay, a two-dimensional case, second axis also needed, right? That's it. You don't need to describe, so y-axis is upward, or x-axis to the right, or left, right. Just draw, and it's enough. Right. Okay, so now this is the ground level, so I position my x-axis along the ground level. Right? So that is my x, that will be my y, right? And as I said, something was, okay, in this case, the arrow was shot at the angle which is given 40. Okay, just let me check it. 45 degrees. 45 degrees. Right? And the travel time is given. So what is given? Angle 45 degrees. And the total travel time. Maybe you know what? Let me label just this point as point B. And then I will just write T sub B. T sub B equals to what? 5.4 seconds. That's it. Nothing else is given. Not much. The question is, in part A, actually part A, draw the situation and introduce coordinate system. Again, there's no point of showing another arrow over here, right? And the origin. Right. Okay. So now what needs to be found? Initial velocity. In part A, we need to find the initial velocity. This v naught. You know what? Maybe I will just write down all those kinematic equations somewhere. Where should I? Okay, I will write them here. First, let me start with y. Vy equals to v naught y. Okay, acceleration, positive or negative in this case? Acceleration due to gravity.
Negative.
Absolutely right. Yeah, negative. Because acceleration due to gravity is downward, right? We cannot change that. So g, and relative to our y-axis, that is the negative acceleration, right? So then minus gt. So don't drop subscripts. Right. And again, this is not the total velocity; it's the y component of the total of the initial velocity. Sorry, of the initial velocity. Then y equals y naught plus v naught yt minus gt squared over 2. And then vy squared equals v naught y squared minus 2g y minus y naught. Okay, so the whole set of equations in the y direction. And then x equals x naught plus v naught xt. So let me frame it, because we will be addressing them quite often now for a couple of problems. So what can be done to find initial velocity? Any hints, any ideas?
The y equals y naught equation, since y and y naught are both 0.
Okay, we can use that equation. And which point? Okay, guys, you need to understand that we can use any point as our final point, right? It can be this point, it can be this. Any point can be used as our final point, and these equations can be used, right? So if you suggest to use equation number 1, so which is your final point? Which final point you suggest us to use? B? Okay, so if we use B, which piece of information do we know about point B? Too much of talking today, right? What?
It's 0 meters, like on the
0. So you're saying that final velocity, no, y component of the velocity, final velocity at point B is 0.
No. I'm not saying that.
You're not saying that because that's what I
I'm
heard.
saying like the
Okay, maybe long
the
day, right?
final-
I'm hearing that.
the final y displacement is 0.
Why this? No, in this case, it's not a displacement; it's just a coordinate. Yeah. And which equation do you suggest to use?
Y equals y naught.
So the second equation. The second equation, right? Can that be used? Okay, we will try this. First one, and again the same question: which point can be used as the final point in order to use the? Okay, another point. So basically, and yeah, pretty much that's what he suggested, right? Okay, so already two approaches suggested, right? So now we just need to look for some additional piece of information which we know, just know, right? Additionally, right? So first, of course we know. Let me start with your approach first, and then we'll go to your approach, right? Because yours kind of a little bit, I don't know, maybe not longer, but okay. I want to start with that. About this point, maximum, so let me label this, it's a y max, right? About that point, let me label it somehow. Actually, I label this point as point A. So, what do we know about this point A? About velocities? Y component of the velocity at point A is 0, right? Because it's just like a one-dimensional motion, right? If you look just from this side, object just goes up, stops for a moment, and then it starts going down. So you need to remember, sometimes this piece of information is quite useful. So let me write it. So Vy at point A equals 0. Everyone sees that. Remember that it's sometimes it can saves you, right? Saves your exam. Right. And so let's use equation number 1. So I will label it 1, first approach. So point A is our final point. And I will use equation number 1, right? So this is 1, 2, 3, 4. Right? Okay. So we can first I will write the equation, the whole thing. Which way? Okay. Ya equals to V naught minus GT at point A. Okay. As you told me, this is 0, and travel time. You already told me, right? So travel time, half of that, right? So in this case, since trajectory is completely symmetrical relative to this point, right? Point A, right? So the travel time on the way up and travel time on the way down exactly the same. Use that symmetry. You remember that symmetry, right? But of course, if you have this situation, for example, right? Something was thrown and it hit some building. Can we use the symmetry? Let's say we know the travel time here, let's say 4 seconds. Can we use the symmetry? Symmetry is broken now, right? It doesn't mean that from this point to that point it will take 2 seconds. No way, right? Now symmetry is broken. You have to be careful, because I see from time to time students still try to use the symmetry. All right. Okay. I think my marker is getting a little bit dry. No, I don't like this. I like chisel. Point. Yeah, this is better. So, and TA equals to TB divided by 2. And I will write symmetry. Yeah. Point B, we will explore all possible solutions, right? Point B, we already discussed, right? But which equation do you suggest to use point B?
I don't know, but I thought the first one like it's not, right?
He suggested to use the second equation, and we're going to use that. But then there's another way. Okay, I will discuss all situations. Right. Okay, so let's finish this. Right. So it will be. Okay, I will rewrite V naught equals to GTA over TB over 2. Right. Okay, so we can calculate it. I will just write down. You can calculate it. I will just write down. Right. It will be 26.46 meters per second. Okay, so it's a first method. Now the second. What gentleman suggested, right? Equation number 2 and point B is our last point. I mean the final point, not the last, right? B, final point, and we're going to use equation number 2. So it will be y at B equals y naught plus v naught yt b minus gt b squared over 2. Right? Yeah.
One of the equations for each is in round velocity is equal to equation B.
That will be another method. We're yeah, one step at a time, right? But yeah, you're absolutely correct. Yeah, you're absolutely correct. But this was suggested before, right? Let's. So this is coordinate 0. This is 0 because it's our ground level, right? YB 0. Agree? Look, this is our B point. What is the coordinate? 0. That's where we position our origin, right? 0, right? So this is 0. Initial position also 0. Both of these points are at the ground level. And so now T sub B can be factored out, right? Okay, if I go over here, can you still see it? Let me bring my gimbal down. Right. So TB, it will be V naught Y minus GTB over 2 equals 0. I just factored out T sub B. Right. Obviously time is not 0 at that point, so this must be equal to 0. Right. V naught Y minus GTB over 2 equals 0. Okay, everything is given. G, T sub B. Right? You look confused. Following? Yeah. Okay. Awesome. So from here we will get exactly the same answer. V naught Y equals to. Yeah, it's the same. GTB over 2. Right. So same. Okay. I will put some happy face, right? It's good to get confirmation. Am I change the right one? Yeah. So now. So we used both of your methods, right? Yours and yours. And now you suggested something. So say it to everyone now.
So at the end,
Final point is B. So what's so special about point B?
velocity is the same one as final velocity is the same one as initial velocity.
Guys, symmetry, to some extent, symmetry in the velocity. Look, if we take, for example, this level, just completely arbitrary level, right, parallel to the ground, what can you say about velocity? Y component of the velocity at these 2 points? Magnitudes are the same, right? But what about directions? Here it's up, here it's down, but magnitudes, absolute values are the same. Remember that, right? It's another trick which can be used, right? So here V sub y up, and here will be the same V sub y down. Symmetry, right? So now everyone agrees. Of course. Right. So now if we compare this point and that point, what about this velocity y component of the velocity? It's the same as initial but negative. So don't forget to use that minus, because these equations will give you rubbish then, right? So negative velocity, right? Okay, so now let's use this technique. So this will be number 3. So now B is our final point again. And which equation we should use, right? The first one will be the easiest, right? But I think it's still possible to use, for example, equation number 3. No. Equation number 3 just gives us this important piece of information. Actually, speaking of that, look, if we write this equation for point B, this and this and this are the same zeros, right? And we will get final velocity at point B, absolute value, equals to the initial velocity at point B, absolute value, right? Right. Okay, but anyway, so equation number 1. And then we use equation number 1. And I will write, so V y b equals to minus V 0y. Right. Okay, so now I will just rewrite first equation of B y b. Okay, and maybe I will frame this important fact just to remember. V sub y, I'm just rewriting, it's V 0y minus gt at point B. And so it will be minus V naught y equals to V naught y minus gt at B. Good? Following? Okay, so now this goes to that side with minus. We'll have minus on both sides, giving us plus. 2 V naught y equals to GTB. Now I'm trying to control myself when I pronounce G. I remember my first year talking too much, so G, J, G, G sometimes, right? And then in my evaluations, one student wrote, G is not equal to J. So after that, I'm trying to really control what I say. Okay, so now from here, obviously we will get exactly the same velocity. Velocity. GTB over 2. So you see, the same result can be obtained using different methods. Right? Yes, so that will give us y component of the velocity. Then, how can we find x component? Well, let's find first the magnitude of the velocity, right? Initial velocity. Let's find magnitude. All right, so now I will separate it, and let's find now v naught. We found y component of the initial velocity. Now let's find the v sub 0. So what can be used? Okay, let's show what we found. So I will just drop the normal line. So this is vx, this is v naught y, this is v naught x, right? Okay, so that's what we found. Be careful, use these equations. Don't just use V naught in those equations. Use components. Use components. Right. Okay, so how can we find V sub 0? Yes, you're suggesting okay. I wanted to ask him, right? So, huh? 10 of 45. I would probably use. Okay, this angle is also 45 degrees, right? So it's a V naught times sine of the angle, right? I will probably use that. Right. So V naught y equals V naught times sine of 45 degrees, and from here we can get V sub 0, right? So from here, V sub 0 equals V naught y divided by sine of 45 degrees. I'm already changed the third marker, and I still cannot find. I have tons of them in my bag. At some point I need to clean and trash. Oh, this is fresh. Finally. Okay, so let me write the answer. This gives us, where is it? 37.42. 37, sorry, 42 meters per second. And the x component you can easily find also, right? But since the angle is 45 degrees, the x component and y components are going to be the same, right? Okay, so V naught x in this case equals to V naught y. But if angle is not 45 degrees, you can just use cosine function anyway, right? Right? So now let's let's write the vector. So it will be, where is it? 2646. 2646 meters per second in the I hat direction plus 2646 in J hat direction. You can also find magnitude we already found. I need to erase something. Or maybe I will write here. I will move to this side. Can you still see it? No? No way. Okay. One method is enough, right, to find. So let me erase this method. Have you managed to write it down? Right. Okay. So now part B, let's find, okay, I will use more. B, let's find y max. Y max, maximum height of this trajectory. Yeah. Ready? Giving the approach. What? What do you sign?
Yeah, so say, like in this equation.
So the equations are here, right? I wrote them down over here, right? So we need to find y, right? Y. So there are basically two options only. Either this or that. Y here and y there. So there are two ways of finding it, right? Huh?
Because I used a different one.
Which one?
I used velocity squared sine squared beta over 2g.
Okay, it doesn't ring the bell, right? We need to look at that, right? Because just if I look, maybe I can recognize it, right? But out of these 4, let's just start with this, right? Because that will be given on the exam, right? On the formula sheet. That's what we need to find. This is 0. That's what we found. Travel time. We know the travel time to point B. It's a half total travel time. We already used that, right? So equation number 2, probably one of the easiest approaches. Or this is 0. This we know. G no. Yeah, also this is 0. This actually may be even easier, right? Maybe, right? Okay, so let's, which way actually I used? Actually, I used both. All right, so let's start using equation number 2. All right, so y max equals to y naught plus v naught y t b. No, a, sorry. Max point is a point, right? And minus gt a squared over 2. And this is 0. You know, I think the third equation will be easier. No time equation, I think, would be easier. Because now I have to, still simple. I will just write down the answer. Because now we just plug number. You just need to plug numbers. Right. This is given part A. Travel time, TA, it's a half of TB, right? Okay. I'm not going to plug numbers. I'm going to just write down the answer. It will be, okay, let me write. TA, it's 2.7 seconds, right? And it will be equal to 35.72 meters. You can round it down to 260. So it will be 36 meters. Then, another option, equation number 3, or so rotational motion. Okay, so yeah, we'll skip this. And one small piece, y component of the final velocity at point B, it's not 0, because some students get confused. They think after collision with the ground, velocity will be 0. But we're discussing only the flight, right? Just before it hits the ground, right? So don't get confused, right? So rotational motion. Okay, here students struggle. Obviously, there will be a problem about rotational motion, and every semester the worst results are usually about rotational motion. Wait, yeah, we don't need this. Right. So it says car engine slows down, but basically just a disc. First, its velocity 3,500 RPM. Which velocity we're talking about? 3,500 RPM. It's an angular velocity, right? It's an angular velocity. So initial angular velocity is given, and then final angular velocity 1,200 RPM is also given. And it decelerates in 2.5 seconds. So we need to find angular acceleration and then total number of revolutions, right? So we have so let me write a car engine slows down, right? Okay, so let me write omega, which way I label it? Omega 1. No, it's let's start with omega 0. It's 3,500 RPM, and then omega 1 is 1,200 RPM. Right, and it happens So let me. So T naught, of course, 0, and T1 is 2.5 seconds. Every time you remember, all those kinematic equations were derived assuming that the initial moment of time is 0. T naught was 0. So we need to find in part A alpha angular acceleration. Yeah. Yeah. Okay, it's just basically what we have, some object which rotates, radius r, positive direction of angular velocity. Huh? Counterclockwise. Positive direction, counterclockwise, right? So let's assume that this is, for example, omega. Yeah, it's a positive omega, right? I just want to remind you. Right. Okay. Right. And yeah, we assume it's spinning this way. Right. So what can be used in order to find acceleration? It's the rotational kinematic equations, right? We also assume that alpha is constant. So let's assume alpha is constant. So it slows down at a constant rate. It slows down at a constant rate. Okay, so which equation can be used? Now equations you see over there, the last set of equations. I think it's obvious, right? Equation number 1, right? For angular acceleration. So equation number 1, so it will be omega 1, it's a final, equals omega naught initial plus alpha t. Right now we don't know the acceleration, so I use plus. But if it's negative, it will appear automatically in this case because we don't know. We don't know acceleration. We need to find it. But before I start plugging RPM, it's very useful practical units, right? But not for calculations. Let's just get rid of revolutions, right? Let's use which radians? Let's use radians. No, revolutions per second. Let me convert to revolutions per second. Because time is given in seconds, so we need to bring them to common units, right? So let me do this. Omega 1, okay, omega 0, 3,500 revolutions per minute. I need to construct a ratio which is 1. You remember? Units conversion. Right? So since I want to get rid of minutes in this ratio must be upstairs. And then of course in 1 minute it's 60 seconds. So again it's just 1. This what we have in these brackets is just 1. We're not changing the value of this. So, but it allows us to cancel minutes. Right, so if you do this, I will just write down the answer. It's omega naught. It will be 58.33 revs per second. And then similar, I can do it for omega 1. Again, it will be 1200 revolutions per minute. 1 minute 60 seconds, and it will be equal to 20 revolutions per second. Okay, and now we're ready to get back to our equation number 1, right? I'm not asking you much because it's quite straightforward. So now alpha will be obviously equals omega 1 minus omega 2 divided by, actually it's a T1, right? T1 Alpha positive, negative, negative, moving negative. Acceleration due to negative. Y negative. Algebra gives us that number. Omega 1, 20 minus 58, right? Okay, let me plug. 20 minus 58 divided by, where is my time? 2.5 seconds. So this will be revs per second equals. So negative, what did I calculate? 15.3. Negative 15.3 units of angular acceleration. Revs per, in this case at least, revolutions per square second. Okay. If you're not sure about units, at least look at your equation and combine and collect all the units which you see there. Right? It will be correct, right? Of course, it can be simplified, but at least you get something. Okay, so now, number of revolutions that this engine completed over this period of time when velocity was going down. So there are two approaches we use to calculate number of revolutions. Now, part B, let's calculate number of revolutions. Right. In this T1. Right. In this period of time, T1. So, which approaches did we use to calculate number of revolutions? Number of revolutions in the period of time from T0 to T1, right? Actually, I want to ask you, of course, right, about one of the approaches related to what we discussed at the very beginning.
Area under the curve.
Yes. Now we know initial angular velocity, we know final angular velocity, we know angular acceleration is constant, so we can plot our graph, right? And if you calculate area under that graph, it will be a number of revolutions, right? Or the second approach, more mathematical approach. Come on. Kinematic equations.
Yeah, wouldn't it be numbers?
Yeah, number 2, theta. What is number of revolutions? It's an angle, right? Just a fancy way of measuring angle. Radians, degree, number of revolutions, right? Or equation number 2. And of course, calculation with area is easy. Okay, so let's do both of these. Right. I will put first method. Area under omega versus time curve. Conservation of brackets. If you open end brackets, you must close end brackets, right? Fundamental law. Right, so if I plot this, omega versus time, right? So what? This is T1. First we had omega naught, here omega 1, and omega naught is larger, right? So the curve should go down, which units I used, radians per second. We can use revolutions, not a big deal. Right. Slightly distorted, I just missed the level of omega 1. Right. Okay, so area is basically this. show that this area under the curve, right? So this area. If the questions were about finding a number of revolutions between this point and that point, of course you will have to find only this smaller area. Yeah. You can integrate it. I explained to you why I don't integrate. Yeah. Because like a gentleman asked, what does that D mean, right? So it's we have different level of preparations, right? And university accepts everyone, and putting calculus based as a result, we have such a disbalance, right, in terms of preparation. But usually after 1 year, everyone gets to the same level. Okay. So number of revolutions equals, right, so what will be, okay, triangle, rectangle, right, 1/2 omega naught minus omega 1 times T1 and plus area of over first triangle, now rectangle, omega 1 times T1. Oh. Process it in Photoshop and send it to me. Right. So you will get, I'm not going to calculate it. I will use calculating second method, 97.9 revs, which is approximately 98 revolutions. You can calculate this. Okay, and the second method, I will separate it like this. Second method, of course, just the equation number 2. It's 2, right? The way I wrote it. Yeah. Theta equals theta naught plus omega naught T1, okay, it will be theta 1, plus 1/2 alpha T1 squared. But alpha, of course, negative, right? We found it. So when we start plugging numbers, of course, alpha is theta naught. It's basically disk, right? We can pick all the time point which we're going to describe point on the x-axis, right? As a result, theta naught will be 0. So theta naught in this case. Or you can say theta 1 minus theta naught, it's actually number of revolutions, right? So it's initial position and difference between this final angle and the initial angle. That is the number of revolutions. So for here I just drop theta naught. Right, and now, yeah, of course, we can plug numbers because nothing else needs to be done. Where is my omega naught in revs per second? This 58.33 revs per second times 2.5 seconds. Right. Then plus 1.2. Acceleration, don't forget it's negative. Where is our acceleration here? Minus 15. Is it 15 point? Yeah. Minus 15.3 radians per square seconds. And time again 2.5. 2.5 seconds. And to the power of 2. You can calculate. And you will end up, of course, with exactly the same number. It will be 98, okay, approximately 98 revolutions. Again, it's like with projectile motion. Just look at these equations and see what you can get and how. few questions right quickly. If you know tangential velocity, can you get centripetal acceleration immediately? And radius is given. Yeah. Just a formula, right? Of course, formula will be given in the formula sheet, right? Again, total acceleration, it's a centripetal acceleration plus tangential acceleration, right? So careful about those two accelerations, right? Because that's a little bit confusing. If you have uniform circular motion, what's the value of tangential acceleration? Uniform circular motion. What does uniform means in this case? Constant what? Uniform, for example, uniform translational motion. What does it mean?
The same direction?
Yeah, but uniform means constant velocity, absolute value of the velocity, right? In this case, if you have uniform circular motion, what is constant? Magnitude of tangential velocity, and of course angular velocity also will be constant, right? So uniform circular motion, angular velocity constant, and of course tangential magnitude of tangential velocity is constant, right? Okay, then it means that what's the value of tangential acceleration? Tangential acceleration describes what? How change of value, right? Absolute value, magnitude of tangential velocity. Pretty much tangential acceleration describes if object moves with a constant, or it accelerates, right? Or decelerates absolute value, right? Moves faster or slower, right? That's what tangential acceleration describes. So if you have uniform circular motion, tangential acceleration is 0. What about, in this case, centripetal acceleration? So we have uniform circular motion. Is centripetal acceleration 0? Never. If you have circular motion, it means centripetal acceleration is not 0. If centripetal acceleration is 0, it means what? No, it means, oh yeah, it's actually also one of the options, right? It means you don't have a circular motion, right? It can be motion along a straight line, or as somebody said, it stopped, right? In this case, everything will be 0, right? Except for position, right? Probably. Right? So be careful, right? If you have circular motion, centripetal acceleration is never 0. Or if somebody tells you, okay, I have a trajectory and I have a centripetal acceleration, it should immediately triggers your brain that trajectory must be circular, right? Because there is a centripetal acceleration. Circular motion and centripetal acceleration, they're like Siamese twins. Impossible to separate, right? But tangential acceleration, it depends. If tangential velocity stays the same throughout the whole motion, magnitude of tangential velocity stays the same, then tangential acceleration is 0, right? Okay, so careful with that. And I guess we need to call it a day. You're tired, I'm exhausted, right? Yeah, 2.5 hours, so that's usually the normal time for the exam. Every session of midterm exams and final exam usually up to 4.5 hours, but sometimes it goes that way.
Thank you.
Okay guys, yeah, if you have any questions, I postponed the homework till Wednesday, but make sure that you solve all problems related to rotational motion.
Bye 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 bye. Ma tu l'amore sul pianeta te lo fai.